Welcome. Today we're going to take a look at how light behaves as it enters different materials or media. We'll be able to explain some things you may have noticed before, such as the fact that objects that are in water may appear broken. This has to do with light passing between water and air. It can cause objects to appear bent or broken, as well as other phenomenon that might initially seem different, like the trapping of light in a fiber optic cable, or the strange appearance of the surface of the water when you are underwater and looking up from the bottom of the pool. We'll be able to understand that as we get into this lecture today. A very helpful way to describe the behavior of light is by using something called the Ray model of light, which is named after a guy named Raymond. No, just kidding. Ray refers to treating light as a stream of particles or a beam of photons. We know that's the name for the particle of light. So if we imagine instead of the wave nature of light, imagine light as a stream of particles. But even if we want to stick with the wave nature of light, we could think about the direction in which the wave is traveling, and the same sort of logic would hold. And so, for example, if you wanted to show light coming out of a flashlight, you could show those waves as leaving the flashlight by drawing some rays. We draw really not a set number of these that you have to draw. We could draw some of these to show the waves of light leaving the flashlight and traveling forward. Or you could, have like a laser pointer or something like that and imagine seeing a single ray traveling outward. Sometimes we'll draw the arrow in the middle of the ray to show that it just continues to extend forward. Another thing we have to keep in mind in order to understand the apparent bending, or the way that light might bend or reflect, is what we talked about in our last lecture, the fact that all electromagnetic waves travel at the same speed in a vacuum. That's an important quantity to remember. Remember that value C is 3 times 10 to the 8th meters per second, the speed limit of the universe. Nothing can travel faster than that. But when light enters a medium or a material, without exception, the speed of light slows down. No one's ever discovered a material that will make light travel faster than c, but other materials will make light travel slower. The new speed of light is then dependent upon the material itself and the way that electromagnetic fields propagate in that material. And we have a way of quantifying this, or describing numerically how much light speeds up or slows down, with this thing called the index of refraction. So this is going to be a number that's going to tell me how much a light speed varies from one material in comparison with a vacuum. We're going to use little n as our symbol for the index of refraction. Now, the index of refraction is defined to be the ratio of the speed of light in a vacuum, c, to v, the speed of light in a material. So this equation, we want to add this to our equation card. We'll use this in our problem solving. So in the numerator, we have the speed in a vacuum, and in the denominator, we have the speed in a material. And since the speed of light in a vacuum will always be the bigger of the two numbers, this ratio is always going to be bigger than 1. However, as the speed gets slower and slower in the material, the denominator gets smaller, the index of refraction will become higher. So as we look at the table here, we can see that in these various materials, that the index of refraction varies, and generally the more dense a material becomes, the higher the index of refraction is. In other words, the slower light travels in that material. So down at the bottom of the list, we have diamond, in which light travels very slowly, in comparison with air. And if we look at air, the number is almost 1. And so for air, we essentially assume the 3 times 10 to the 8th meters per second is effectively also true in the air. There isn't a dramatic slowing in that material. So let's look at a couple examples of how this formula might be used to solve a problem. So the first question, we're asked to find the speed of light in flint glass. So we look on our data table and we see that flint glass has an index of refraction of 1.62. Slows light down by that factor. So since index of refraction is equal to the speed of light in a vacuum divided by the speed in the material, we can substitute the numbers into the equation. We put 1.62 in for n. We put 3 times 10 to the 8 power for the speed of light in a vacuum, c, and we solve for the speed v in the material. We use our calculator to solve this. We get 1.85 times 10 to the 8th meters per second, which is still very fast, but it is noticeably slower and will cause some effects to the way that light travels through that material, as we'll talk about later. If you ever get a number bigger than 3 times 10 to the 8th meters per second, then you made a mistake someplace. That can't be. In the second example, we are asked this time to find the index of refraction for material glycerin, knowing that light travels at a given speed in that material. So here's a little more straightforward. Again, n is the ratio of the two speeds. So we put in 3 times 10 to the 8th in the numerator for the speed in a vacuum, and then the speed in the material, 2.04 times 10 to the 8th meters per second, and plug and chug, we get 1.47. So there's no unit to the index of refraction, it's just a ratio between two speeds. Alrighty, now that we have different way, or a new way of quantizing how light travels in a different material, let's think about what happens when light strikes a material, because it's a little bit more complex than simply having light change its speed. In fact, a number of different things can happen. And we saw before when we talked about mechanical waves, when they run into things, a boundary or a change in medium, there were 3 possibilities. And the same 3 possibilities, and oftentimes all will happen at the same time, a little bit of each, will happen to waves of light as well. Sometimes some of the light energy is absorbed, is dissipated in the material and disappears. We'll find often sometimes if the light energy is reflected, and we'll have waves bouncing off of surfaces. And then thirdly, we'll have light being transmitted, which is what the index of refraction is really useful for, because then we go into the new material and we change to a different speed. So let's take the first example, that of absorbing of light. And you might ask the question, how do we tell if a material absorbs light? And a lot of times looking at whether the material is white or dark colored, or light or dark colored, can tell us that. A black shirt is black because as light strikes it, it's absorbed by the material, and very little bounces off the material for your eye to see, and so it looks black. Whereas a white shirt is actually very reflective. Most of the light is bouncing off of that material. Now this might raise an interesting question. There are different kinds of black, like this shoe right here in the picture. We might have some flat black and some glossy black. And if black doesn't reflect a light, then what's the difference between the two? Really the reason why you're seeing light bouncing off of the glossy portion of the shoe is there's a thin clear film on top of the glass, and that thin clear film is reflecting the light. It's not giving us any color, but it's reflecting the white light back to us. Maybe more to come on color later. This also raises an interesting question then. If white is a material that reflects light, and is why I see it as light colored, what's the difference between a white wall and a mirror? A mirror, of course, reflects light and allows you to see an image, but a white wall reflects light as well, but we don't see an image or a reflection in the white mirror. So what's the difference between those two? Well, the short answer is that there are different kinds of reflection. So you can see down here in this example, we can see these rays of light striking a smooth surface, and all 4 rays come in an orderly way, and they all bounce off in the same orderly way. So whatever object this light's coming from, it's going to bounce off, and the orientation of the light looks exactly the same. And so we see the reflection of that object in the smooth surface, or the mirror. So this picture might represent the mirror. However, the wall has some texture to it, and since even might seem smooth to the eye, when we look at closely compared to the mirror, it has some texture to it. So those same 4 rays hit the wall, and they bounce off kind of every which way. And we know we can still see light, we get the light from it, but we don't have a clear image from that. So the terminology for this, for the smooth mirror, is called specular reflection. It all bounces off nicely. And on a rougher surface is called diffuse reflection, where it scatters in such a way that we don't have a clear image afterwards. Now it's very hard to predict what will happen when you strike a rough surface. However, we can easily predict, using the law of reflection, what happens in the case of specular reflection, where all those rays bounce off nicely in the same way that they came in. So let's consider that we have a smooth surface. Here's my surface right here. And I have a ray, a beam of light, a stream of photons or particles, a beam from a flashlight or a laser pointer, or maybe some light from the sun, and it's going to strike that surface. So maybe it's a puddle or something, a smooth surface of the water. And what we say is that that ray of light has an angle that it strikes the surface with. And now we could measure the angle it makes with the surface itself, but by convention, we'll see that later on this is going to be pretty convenient, is we're going to draw what's called a normal line to measure all of our angles from. Now, the word normal mathematically means perpendicular. If you remember, the normal force was perpendicular to a surface. So we draw a line that's perpendicular to the surface, and then from there, we measure the angle that it strikes the surface. So this is the angle that it strikes with. We call this theta sub I. And theta sub I goes by the name of angle of incidence. Angle of incidence. We say that light is incident upon the surface at that angle. And then after it hits the surface, it's going to bounce off. It's going to be reflected off on the other side of the normal. And with specular reflection, it's really kind of nifty, but the angle of incidence ends up being exactly the same as the way that it bounced off on the other side. And this theta sub r is going to be our angle of reflection. And again, this is supportive of this wave particle nature of light, because if you threw a basketball or tennis ball against the floor, the same thing would be true. If you bounce it off, hits the floor at a 30-degree angle, it bounces off at a 30-degree angle as well. So we can say theta sub I is equal to theta sub r. This is the law of reflection.